Alternating current. முதல்ல இந்த ஏசி கரண்ட் சாப்டர் நம்ம ஆரம்பிக்கிறப்போ டிசி கரண்ட் என்ன, ஏசி கரண்ட் என்ன, ஏசி கரண்ட்டுடைய மிக முக்கியமான பெராமீட்டர்ஸை டிஃபைன் பண்ணக்கூடியதும், ஃபேஸ் அப்படின்ற ஒன்றை இன்ட்ரடியூஸ் பண்ணி, ஃபேசர் அப்படின்றத ஒன்றை இன்ட்ரடியூஸ் பண்ணி, ஃபேஸ் டிஃபரன்ஸ்னா என்ன அப்படின்றதெல்லாம் பார்த்து ஒரு இடத்துல நிறுத்தி வச்சிருக்கோம். இப்போ 2 சாப்டர்ஸ்ல இது மிகப்பெரிய ஒரு தாக்கத்தை ஏற்படுத்துது. நம்பர் 1 ரெசிஸ்டன்ஸ், கெப்பாசிட்டன்ஸ், இண்டக்டன்ஸ். இது 3 பாசிவ் எலிமெண்ட்ஸ் சொல்றோம். இந்த செமிகண்டக்டர்ல இருக்கக்கூடிய டயோடு, டிரான்சிஸ்டர், இந்த 2 கருவிகளும் ஆக்டிவ் எலிமெண்ட்ஸும் சொல்லப்படுது. இவை இரண்டுகளும் சேர்ந்து பல்வேறு விதமான செயல்பாடுகள்ல ஏசி சர்க்யூட்ல செய்யுது. இப்போ சாப்டர்ஸ் எல்லாத்தையும் விளக்கி வச்சுட்டு நம்ம என்ன புரிஞ்சுக்கணும்னாக்க, ஒரு ரெசிஸ்டன்ஸ் டிசி சர்க்யூட்ல எப்படி வேலை செய்யும், ஏசி சர்க்யூட்ல எப்படி வேலை செய்யும், ஒரு கெப்பாசிட்டன்ஸ் டிசி சர்க்யூட்ல எப்படி வேலை செய்யும், ஏசி சர்க்யூட்ல எப்படி வேலை செய்யும், ஒரு இண்டக்டன்ஸ். நல்லா கவனிங்க, எலக்ட்ரோ மேக்னெட்டிக் இண்டக்ஷன்ஸ்ல நம்ம ஒரு இண்டக்டன்ஸை பத்தி படிச்சோம், செல்ஃப் இண்டக்டன்ஸ், மியூச்சுவல் இண்டக்டன்ஸை பத்தி படிச்சோம். கரண்ட் எலக்ட்ரிசிட்டில ரெசிஸ்டன்ஸை படிச்சோம், கரண்ட் எலக்ட்ரிசிட்டில ரெசிஸ்டன்ஸை படிச்சோம். அப்போ எலக்ட்ரோஸ்டாட்டிக்ஸ்ல கெப்பாசிட்டன்ஸை படிச்சோம். இப்போ இந்த 3னுடைய டிசி சர்க்யூட் பிஹேவியரை முதல்ல பார்க்கிறோம், ஏசி சர்க்யூட் பிஹேவியர் அப்புறம் பார்க்கிறோம். இதனுடைய காம்பினேஷன் ஆஃப் சர்க்யூட்ல எப்படி பிஹேவ் பண்ணுதுன்றதை பார்த்துட்டோம்னாக்க இந்த சாப்டர்ல மிக முக்கியமான ஒரு மைல்கல்ல தாண்டோம். இப்போ முதல்ல நம்ம என்ன பார்க்கிறோம்னாக்க, கரண்ட் என்ன, ட்ரிஃப்ட் வெலாசிட்டினா என்ன, கரண்ட் டென்சிட்டினா என்ன அப்படின்னு பார்க்கிறோம். அதாவது செமிகண்டக்டர் பிசிக்ஸ்ல பேண்ட் தியரியில மிக முக்கியமா ஒரு விஷயத்தை பார்த்தோம். என்ன அப்படின்னாக்க, ஒரு மெட்டீரியல் அப்படின்றது எலக்ட்ரிக்கல் கண்டக்ஷன்ற ப்ராப்பர்ட்டியில ஃப்ரீ எலக்ட்ரான் இருந்தா கண்டக்ட் பண்ணுன்னு பார்த்தோம். அந்த ஃப்ரீ எலக்ட்ரானை ஒரு பாயிண்ட்ல இருந்து இன்னொரு பாயிண்ட்டுக்கு நகர்த்துறதுக்கு பேரு பொட்டன்ஷியல்னும், பொட்டன்ஷியல் டிஃபரன்ஸ் இருந்தா நகருன்றத பத்தியும் கரண்ட் எலக்ட்ரிசிட்டில நிறைய பார்த்தோம். இப்போ 3 டேர்மை பத்தி பார்க்க போறோம். கரண்ட்னா என்ன, ட்ரிஃப்ட் வெலாசிட்டினா என்ன, கரண்ட்டுக்கும் ட்ரிஃப்ட் வெலாசிட்டிக்கு என்ன ரிலேஷன், I is equal to NAVDE, அந்த ரிலேஷனும் கரண்ட் டென்சிட்டியை பத்தியும் அறிமுகம் பார்க்க போறோம். இப்ப நம்ம பார்க்கிறது முற்றிலுமாக டிசி சர்க்யூட்ஸ்.
All right, our next unit is on direct current and DC circuits. So in this video I'm going to tell you about current, drift velocity, and current density. So let's first start out with a definition of current density, or excuse me, a definition of current. If we have a wire, this is a wire, this is the cross section of the wire. Here are some electrons, we'll say, that are moving. Now electrons, when they move through here, they don't move in a straight line when they move through a wire. They get going when you put an electric field, say the electric field's heading that way. Well, if there's an electric field heading to the left, then the electrons start moving to the right, but they bounce into particles along the way. So they take these weird paths, but they do drift. You know, even though they don't go straight that way, their general direction is down the wire, but only at centimeters per second, not you know what you might think of, you know, hundreds of meters per second or faster. They go very slow, they drift along. Well, in any case, the current is going to be equal to, we're going to designate current with an I, just like you did last year, and that is going to equal the amount of charge, these charges that go through a cross-sectional area per given time. So that's average current, the amount of charges that actually go past that cross-sectional area. Of course, we have an instantaneous currents too, and that would be, as you might guess, dq dt. Okay, so the numerator is the amount of charge that passes through the cross-sectional area in a given time t. So that means that the units for current are going to be coulombs per second. So a coulomb per second that's equal to an amp. Or we can, that's equal to an amp. Okay, so that is what current is all about. Now let me tell you what current density is all about. Sometimes we want to talk about the current density, and what we mean by that is just how dense the current is. So it's the current per cross-sectional area. Okay, so it's the current density. We're going to designate with a J. That's going to represent current density. And that's J is going to be equal to the current per cross-sectional area. So that would be the units for that would be amps per square meter. That's what current density is measured in. Amps per square meter. Sometimes we abbreviate an amp with just an A, capital A. All right, so that's current density. Now, one other thing I would like to show you is that there's an equation that relates drift velocity, how fast these things drift along, to current. And so I want to show you that. So imagine, if you will, that we have this volume in this wire of two cross-sectional areas, this cross-sectional area and say this cross-sectional area. And let's say that in a time t, all these charges that are in this cross-section move from here to out of there. They actually go past there. So in a time t, then, if in a time t, these all of them, the very last ones are gone. They passed this, they were here in this region, and now they go by this cross-sectional region. Okay, well, I'm going to say that all occurred in a time t, and the distance here, we could call that x, or delta x. Now come on over here with me and let's talk about drift velocity and delta x. I'm going to use this little patch of area here. Okay, so if drift velocity for an electron is how far it goes on average per time, then if I multiply the drift velocity times the time, that's how far it's going to go. So you see this delta x right there? That delta x is VD delta t. That's what I'm going to tell you it is. And so now let's talk about an equation that relates drift velocity to current. Okay, since I is the amount of current that passes through in a given time, let's create one other quantity, and that is the quantity that we're going to create is going to be designated with an N, and it's going to be called the charge density. N is equal to the amount of charges in a volume. Amount of charge per volume. Or charge carriers per volume. And so in that time, you see, if I wanted to know just how much charge passes through here in a given time, all this charge that passes through there in a given time, that would be current. And so the amount of charge that passes through there is just how many particles there are in there. So that'd be N times the volume, because N times the volume is the amount of charge. So N times the volume, and I'm going to write that out because I don't want you to think that's velocity. N times volume is the amount of charge passing through Okay, now, but that doesn't tell me I also need the charge on each one. So the charge on each one we're going to say is Q. So if these were electrons, Q would be 1.6 times 10 to the negative 19th coulombs. See, that is the total charge then. Total charge is the density times the volume. That gets you the number. This is just going to give you the number of charges, but then you have to multiply it by the charge of those charges, and then divide it by time. Okay, one more time, because that's kind of weird, is that you're going to take this is the number of charges per volume, times a volume gives you the number of charges, times the charge on the charges, and that gives you the total charge. That gives you delta Q divided by time. Okay, well then I is equal to N times the volume. Now the volume we're talking about is this volume. And this volume is going to be this area, A, the cross-sectional area, times this width, because isn't the volume of a cylinder the area of a circle times the height of the circle, or whatever that dimension is? So it's going to be A delta X. So it's going to be A, the cross-sectional area, times delta X. Now delta X is the drift velocity times time. So this right here is the volume. The bracketed thing is the volume. This bracket is volume. That's the cross-sectional area, and that's going to be a distance. Drift velocity times time. Times Q all over delta T. That gets you the charge. Okay, now this is a delta T too. I wrote this as delta T and that is delta T, but that's going to just cancel out. The T and the T are going to cancel out. And so this is going to be N times A times VD times Q. So the current that's flowing through a wire is equal to the volume the amount of charges per volume times the cross-sectional area times the drift velocity over the charge per giving. This is normally going to be the charge on an electron. Okay, look at what current density is. It being I over A, it's going to be equal to NAVDQ all over A. And so the A cancels out the cross-sectional area, and the current density is just going to be N times the drift velocity times the charge for one electron. All right, lots of number juggling. See.
Current அப்படின்றது rate of flow of charges. Current densityன்றது I by A. Charge densityன்றது number of charges per unit volume. இப்ப 4 டேர்ம் புரிஞ்சிருக்கும். கரண்ட்னா என்ன, கரண்ட் டென்சிட்டினா என்ன, சார்ஜ் டென்சிட்டினா என்ன, ட்ரிஃப்ட் வெலாசிட்டினா என்ன, கரண்ட்டுக்கும் ட்ரிஃப்ட் வெலாசிட்டிக்கும் உள்ள ரிலேஷனை பத்தி இப்ப பார்த்தோம். I is equal to dq by dt, J is equal to I by A, drift velocity relation எழுதுனா NVDE, I is equal to NAVDE, அந்த Qக்கு பதிலா E போட்டோம்னாக்க NAVDE, I by A is equal to J நாக்க NVDE. Charge density ன்ற டேர்ம் ரொம்ப நல்லா புரிஞ்சுக்கணும். நம்பர் ஆஃப் சார்ஜஸ் per யூனிட் வால்யூம். இந்த 5 பாயிண்ட் முதல்ல இதுல தெரிஞ்சுக்கிட்டீங்களா? Now we are going for the next. Resistance அப்படின்றத பத்தி பார்க்கலாம்.
Okay, I wanted to tell you about resistivity, resistance, and conductivity in this particular video. But before I do that, I just want to go back and just summarize what we did in that last video, because I finished pretty quickly. So here are the equations that we got out of the last video. Current, which is I, is the amount of charge that passes through a cross-sectional area of wire in a given time. So that's average current. And then you have instantaneous current, which is the derivative of Q with respect to time. Kind of like how average velocity is delta x over delta t, and instantaneous velocity is dx over dt or ds dt. Then the same thing with this. One is the average is a delta, and the instantaneous is an actual derivative. Okay, and then from there we also defined current density as the amount of charge that passes through a cross-sectional area. So this is the charge passing through a cross-sectional area. So this is called current density. And we also learned that I is dependent on the drift velocity. By this equation, it's going to be N Q drift velocity times A. So this N is the amount of charges. This is the number of charges per volume. The Q is the amount of charge. The V is the drift velocity. So that would be a small number, maybe a few centimeters per second. And the A is the cross-sectional area of the wire. You can combine this equation with that equation, and then you can get that I is equal to, when you throw this in for I, the A cancels, and you just get left with NQVD. All right, so there you have it. I guess let's just see how this gives you coulombs per second when I put all this stuff together. Come on down here. Come on down here and let me show you that. So N is going to be the number of charges per volume. So the number per volume, the number won't have a unit on it. It's just an integer of charges per volume. So that'd be per cubic meter. The Q would be the amount that would be measured in charge. So that would be in coulombs. The drift velocity is meters per second. And the cross-sectional area is meters squared. So these meters squared and meters team up to cancel out the m cubed down here. And you see how we have coulombs per second, which is the unit for amps. Okay, so back to the original topic of this video, resistivity, resistance, and conductivity. Okay, resistivity is a property of a material that tells you how easily it, or how much it resists the flow of charge, the flow of current in it. So the resistivity of a metal tells you how much it resists the flow of charge. We're going to designate that with a rho, and I know we've already used rho, but we have to double up at this point because we have so many different variables. So rho is going to be the resistivity. And we're going to define resistivity as the amount of electric field that you need in order for you to get 1 amp per square meter of current density. Okay, so it's the amount of electric field per 1 amp per square meter of current density. Okay, so like silver has, you can go and get the resistivity of silver, and at room temperature. Now, the temperature is going to affect resistivity, but that's about it. Nothing else is going to really affect resistivity except for temperature. But if you're wondering what the resistivity of silver is, it's 1.72 times 10 to the negative 8th, and the units are going to be ohm meters. But I don't like those units, ohm meters. I would rather say that it's 1.72 times 10 to the negative 8th, and then put the units that make sense. Newtons per coulomb, that's the field you'll need to get 1 amp per square centimeter of current density. So silver is a very good conductor of electricity, so it has a very low resistivity. And so look, you only need this much field, 10 to the negative 8th newtons per coulomb, to get like this huge amount of current, 1 amp per square meter. That's actually not that much current density, but 1 amp per square meter. If you want that to be the current density in silver, that's the field that you'll need to set it up. Okay, so let's compare that to the resistivity of quartz. The resistivity of quartz is a lot larger. It's 75 times 10 to the 16th newtons per coulomb amps per square meter. So if you want 1 amp per square meter, you'll need to put that much field. That's a lot larger. The other one was 10 to the negative 8th. This is to the positive 16th. So quartz, you really need to up the electric field like a whole lot just to get the same current density. So quartz is not a very good conductor of electricity. Speaking of which, I was going to tell you about conductivity. I'm going to skip resistance for a second and go right to conductivity. So conductivity, we don't use it too much in here, but you should know that conductivity is just the reciprocal of resistivity. So conductivity is equal to 1 over resistivity. We won't give a letter for it. Well, I guess you could call it C if you wanted to, lowercase c, is equal to 1 over rho. Okay, so a material that has a really, really good resistivity has really poor conductivity. So what does silver have? Is silver have a really high conductivity or a really high resistivity? Yes, silver has a really high conductivity. Okay. So there you go with that. And I think I'm going to leave resistance, talking about resistance, I think I'm going to leave that for the next unit. So I'll see you, or excuse me, not the next unit, the next video. So
அப்போ கரண்ட்னா என்ன, கரண்ட் டென்சிட்டினா என்ன, சார்ஜ் டென்சிட்டினா என்ன, ட்ரிஃப்ட் வெலாசிட்டினா என்ன, கரண்ட்டுக்கும் ட்ரிஃப்ட் வெலாசிட்டிக்கு ரிலேஷன், கரண்ட்டுக்கும் கரண்ட் டென்சிட்டிக்குள்ள ரிலேஷன்ல ட்ரிஃப்ட் வெலாசிட்டி வச்சு என்ன ரிலேஷன் பார்த்தோம். இங்க ரெசிஸ்டிவிட்டியும் கண்டக்டிவிட்டியும் பார்த்திருக்கோம். இங்க ரெசிஸ்டிவிட்டியும் கண்டக்டிவிட்டியும் பார்த்திருக்கோம். இப்போ இந்த ரெசிஸ்டன்ஸ்ன்ற மூன்றாவது ஃபேக்டர் பார்க்கலாம்.
Okay, so I want to talk to you about resistance here. You worked with resistance a little bit last year, enough to know that it's measured in ohms. And so let's take a look at resistance. You know how resistivity is the electric field per current density. And electric field is the voltage divided by the distance only for uniform fields. But in our wire, there is going to be a uniform field. At least we're going to say there's a uniform field. So here's our wire. And let's have the field be this way. A uniform field that way, and that's why the electrons head against the field. And if the electric field is this way, and this distance we're going to call D, we'll call that an uppercase D, I suppose, then the voltage between here, between A and B, the voltage between those 2 points, the voltage between A and B is going to just be ED. Okay. Which potential is at higher? Which of these is at higher potential? Well, let's go against the field, and so this would be the higher potential because this is the electric field. So to push a positive charge against the field, that's how you raise potential. Okay, so but the potential is going to be ED. So let's head on back to here. Okay, so since this is electric field and that's electric field, let's set rho J equal to V over D. And you know what? I'm going to call this L. You'll see why. L is just the length. So it's V over L, the length. And so, but J is I over A. Okay, and so let me bring the L over here. And so if I bring the L over here, it's going to be rho L over A times I is equal to V. Now, do you remember last year there was a law called Ohm's law that said that the voltage across a resistor was equal to the current through the resistor times the resistance of the resistor? Well, the voltage is equal to I times R. So here's the deal, this is R. That expression, rho L over A, is R. So the resistance of a metal depends on the following things. The resistance of a metal depends on what it's made out of, definitely. And if you're, it also depends on how long the wire is. The longer the wire is, the more resistance it's going to give to the flow of current. So that's going to give you, if you have a really, really long wire, you're just going to add a lot more resistance to your current. And then A is the cross-sectional area of the wire. So if you want to have a lot of resistance, then you make your cross-section really, really tiny, and you'll get a very big resistance. And so that's the formula for resistance. Now you might say, hey, I know also resistance depends on temperature. How come temperature is not in there? But the temperature is related to the resistivity. So the resistivity is a function of temperature. Turns out that it's usually the case that the colder something is, the less resistivity it has. Okay, we'll talk a little bit more about that later. But yeah, if you're wondering where temperature is, it's in there. But we're going to assume in this unit that the rho doesn't change with temperature. We're just going to deal with things at room temperature. Okay, so that is the equation for resistance. And as I said, I gave you Ohm's law, but let's just define Ohm's law right now. Ohm's law is obeyed for a lot of resistors. In fact, we call resistors where Ohm's law is obeyed, that obey Ohm's law, we call those resistors ohmic resistors. Okay, an ohmic resistor is one that obeys Ohm's law. Just like all springs don't obey Hooke's law, not all resistors obey Ohm's law. But here's the thing, let's put some subscripts on the voltage, the I, and the R, because those subscripts are kind of important. So it goes like this. If you would like to know the current through a resistor, I is the current through a resistor, current flows through resistors. That will equal the voltage drop across the resistor. Voltage doesn't flow through a circuit. It is dropped across different elements in a circuit. So the voltage across the resistor divided by the resistance of the resistor. And that's just the resistance of that resistor. Okay? So this is called Ohm's law. All right, I'm going to cut this video short. We'll call it a night. Thanks, bye. Okay, so I want to talk to you about...
நம்ம மூணு விஷயங்களை பார்த்திருப்போம். I is equal to dq by dt. Current னு சொன்னதுக்கு அப்புறம் current density சொன்னோம். J is equal to I by A. Charge density. Charge density ன்றது n, number of charges per unit volume. இதை ஒன்று பார்த்தோம். R is equal to rho into L by A. Resistivity is equal to E by J. Conductivity is equal to 1 by resistivity என்ற ஃபார்முலாவோட வந்து நின்றுக்கும். தொடர்ந்து பார்க்கலாம். ரொம்ப இன்ட்ரெஸ்டிங்கா இருக்கும். புக்ல நம்ம படிச்சதுக்கும் இதுல உள்ள ரிலேஷன்ஸையும் இப்போ ஓம்ஸ் அந்த ரெசிஸ்டன்ஸுக்கான ரிலேஷன் டிரைவ் பண்ணி காமிச்சாங்கல்ல, இதெல்லாம் ரொம்ப இன்ட்ரெஸ்டிங்கா இருக்கும்.